try to transect right where the optic nerve is, but whether we get that or not, we don't know. So I'm going to go this way, just to help me get this far.
Why is it so like rough? Like tough. Like a little sushi
The
roll.
cornea and the sclera, folks, are dense fibrous connective tissue. They are just the outer fibrous tunic, and we know what fibrous connective tissue looks like. You drew it. Okay, so I'm going to see what I got here in terms of the optic nerve. Okay, then I'm going to go completely around this direction. Now, what lies behind the iris, folks? It's called the lens, and the lens is not in any of the tunics. The lens is not part of the middle vascular tunic. It's not, of course, part. So it's kind of in between. And here I need my knife again, so I'm just going to kind of, just to kind of help me. It's so dense. In fact, when in accidents, if you pierce the outer fibrous tunic, then your eyeball can collapse, and you lose the fluids. Okay, so folks, what I'm doing is I've transected the oculus, and now I'm going to. You're seeing the lens. You're seeing the lens. Why is the lens not just sloughing and floating around?
Because it's held in place.
Because it's held in place by what are called the zonular fibers. Now, unfortunately, I've pulled so hard on this left hemisection that I did sever the zonular fibers. And remember, in the eye, everything goes 360 degrees around. But on this right side, that lens is still held in place by the zonular fibers, which, and I want you to, I want to pass this around again. Now just let me do this part first. Notice behind the lens, see that gelatinous fluid?
Yeah.
Folks, that's vitreous humor. And that's produced once in your lifetime, and that's prenatally. So the cells that make that are gone and never come back after you're born, so that if you get an eye injury and that vitreous humor is ever lost, you can only ever have it replaced with a synthetic substance, and that's why a lot of people lose the eyeball. Yeah, you see how gelatinous the vitreous humor is? Like a jellyfish. It's very gelatinous. Cool. And the purpose of vitreous humor is to hold the choroid layer up against, hold the retina up against the choroid layer. Yeah, and I'll explain that in just a minute. So I digress because I just wanted you to see that fluid first. And you can see even the fixative, which has eroded some of that gelatinous stuff, it hasn't eroded it completely. And look how totally gelatinous it is on that cross-section right there. See, it hasn't, become, yeah. So, back to the zonular fibers, a.k.a. suspensory ligaments of the lens. What I want you to see is when I birth this lens out of here, and I will just sort of pull it out. I'm having to really pull hard. And I want to hold this up. And I want you to see that this is a structure that's called biconvex in shape. In other words, it's convex on its anterior surface and on its posterior surface. Here's the posterior over here. And it's more convex posteriorly. Okay? I want everyone to see, even on our models, and I won't touch them with my
hands. Is that tough, like a marble?
This is made of proteins called crystallins, and they layer like an onion. Mm-hmm. Yeah, and yes, it's very dense, yeah, but it's living tissue, and it's replaced, and you can get little debris in there, and there's phagocytic cells that kind of come in, and we know what cataracts are, is when there's not enough of the phagocytes to munch up the debris, and then you end up with little debris posits. Yeah, so in any event, and those are cataracts. So it doesn't matter if it drops, because you can really see that this is more convex posteriorly than anteriorly, and yet it's referred to as a biconvex shape. Okay, very good. So that's the lens. Now, the zonular fibers of the lens, folks, are ligaments that extend from what's called the ciliary muscle. Now, I'm going to show you the ciliary muscle. We have to kind of look. I'll finish cutting this in half now. And again, like I say, I've headed for the optic nerve, and I hope I get it, but I'm taking my chances here.
Garbage.
Oh, I got it. I don't I want to scrape this on the... Okay, hang on. We're just going to do one more little cut. Okay, ooh, look at that beautiful optic nerve.
Nice cut, Mary.
Nice, isn't that nice? So nice. Okay, so now I know this is awkward, but okay. So folks, here's the iris. It's because it's only half. But now, do you see right behind the iris? There's see that little ruffle of black that goes. And what I'm going to do is I'm going to birth out the vitreous humor on this one side. Whoops, there's the choroid with it. Ooh, this is perfect. Okay, the vitreous humor. Oh, and it. Hang on just a second. It'll hang together. The vitreous humor should hang together. Oh, okay, hang on.
Who would know, though? That's just so cool.
And it's held in place by little fibers too, and this is really hanging together nicely. We usually don't get this good, because folks, what's that anterior-most margin of the retina called? Who remembers? There's the vitreous body coming out as a body. Okay. Now, folks, please look. See this very filmy kind, and there's a little air bubble. That's the retina. That retina is so what's called friable. If I even touch it, it'll just wrinkle up. But see, there's a little air pocket behind it. But the retina, what's the anterior-most margin of the retina called, folks? Do you remember the term ora serrata? The ora serrata, meaning the serrated halo. That retina doesn't come all the way behind the iris because incident light waves, the soonest they can land on the retina in a straightaway direction is behind that ora serrata, and you're just not going to waste nervous tissue, as expensive, as, so to speak, as it is. So there, now I'm going to kind of wrinkle the retina, and what's that real black layer behind it? What's the second tunic? Here's the choroid, and I'm going to grab the choroid. See, I can just grab it. There's the choroid. See that black layer? And then there's the sclera, is the white. So we have our three tunics represented. Okay, so there's the retina. I just sort of scooched it out of the way so that I could then. I mean, you've looked at insides of cameras, have you not? They have that almost velvety black lining to them. That's the choroid, folks. Whose anterior margin? Here's the choroid layer. That forms a continuous black. It's very dark pigmented. Why? Because once light waves get in there, it forces them to jump around and stimulate the photoreceptors called rods and cones. There's the choroid. Now the anterior margin of the choroid makes for the iris and for what's called the ciliary body. And so I want you to see that the ciliary body is like striated, and if you're looking at the posterior aspect of the iris, and you have to catch the light just right, but there's a whole bunch of like striae, like lines, and the ciliary muscle, the little ciliary processes are these little wavy things at the end of the ciliary muscle, and folks, it's the little ciliary processes that make your aqueous humor by a filtrate of blood. They're not secretory cells. They don't make the fluid themselves. They just allow for filtration of blood to make that aqueous humor in the anterior cavity. So there's the ciliary processes. You're looking behind the iris right there, okay, and then you can account for your three tunics. Now, if I were on this side, I've just kind of missed the actual what's called optic disc. Is the place on the retina where all the axons of the photoreceptor cells called rods and cones. And if each of us represented a photoreceptor in our retina, and we'll say this room would be filled with people, each one of us would be part of the population of photoreceptors in the eye, which, by the way, the fovea centralis of the macula lutea, that's the area where there's just cones. It's called the area of greatest visual acuity in the eye because when incident light rays actually land right there, you have your best, sharpest vision. Visual acuity is sharpness of vision. You see the clearest because there's just cones there which discern colored light, and you see your best interpretation of color and shape and crisp edges and so forth. From there, in concentric circles, you get more and more rods until eventually, as you get out to the ora serrata, there's nothing but rods.
Is that why your
Which is for
peripheral vision is
not as crisp. Right, very good, exactly, because it's not landing on that fovea centralis or near it. Yeah, the near, and you'll see some people who really want to see something, they'll kind of come up and they'll kind of tip to their good side so that incident light wave, that macula lutea is always lateral
How come people are left and right-eyed?
We just kind of, it's a learned behavior. It's like our
Okay,
handedness.
like a habit.
It's more habit than anything else,
Okay.
but there's a tendency. Researchers are finding out there are tendencies towards that anyway. But you can force somebody, or you lose your right hand and you're right-handed, you can learn everything with your left. And so, like I say, it's more habit than anything else. So folks, if I were to scooch the retina, if I were to just completely scooch it up, on this left half section, I didn't get right where the optic nerve. Oh, our analogy is, if each of us is a sensory receptor cell, then our long axon from that, all of our axons would exit, let's pretend there wasn't a door back there, could only ever exit out this one door. So this is an area on the retina where it's no sensory receptors, it's just the place where the axons leave to form the optic nerve out here. So can you just, if light lands on the optic disc, it's called, or blind spot, can you see anything at all? Nothing. That is your blind spot, folks. And there's a place where incident light waves land right where the optic disc is, and you can't see that object. Not just in driving, there's a blind spot, but you can, you can't do it for yourself.